All right. Hi, everyone. Thanks for sticking around. My name is Gunnar, and welcome to this session, Performing Chaos in a Serverless World. So the abstract of this talk is that chaos engineering as a field has been used for quite many years now when it comes to traditional infrastructure and containers. But the question is how it works when we're moving to a serverless world where we're using functions and fully managed services. So this is the agenda. We'll start off by looking at what chaos engineering is, not specifically for serverless. Then we'll look at what the motivations behind using chaos engineering is, how to run chaos experiments, and what the challenges we see are when using chaos engineering for serverless. And lastly, we'll look at some chaos experiments and how to run those for serverless. So this is me. A comment I received in the feedback from reInvent was that I talk too much about myself. So when I stopped crying, I decided to keep it short. So I work as an evangelist at Opsio. I have a background in lots of fields. I have 3 kids, and I work a lot with user groups and conferences in the Nordics. That was short, right? So, what is chaos engineering? Chaos engineering is not about breaking things. That's something you hear quite often, breaking things on purpose. That's how chaos engineering is perceived. But it's really not about breaking things. It's more about learning things. Breaking, well, sure, we do break things when using chaos engineering, but that's not really the purpose of it. And we often also hear that chaos engineering is only for production. You should use chaos engineering in production, but that's not really the case either. You can use it in test environments, you can use it in development environments, and so on. As close to production as possible, of course, because using real data, using a system that is under load will probably give you better results, but you don't have to use it in production. And chaos engineering is not only for the big streaming companies. And why I say that is that Netflix is the common example of using chaos engineering. They started the field back in 2013-14, but we can use it in more or less any type of development environment or any type of system. So chaos engineering today is used by companies ranging from small startups up to big fintech and financial companies. And chaos engineering helps those companies get environments that work better and are more confident in how the system works. So these are the principles for chaos engineering. Were written by a team from Netflix when they created what's called chaos engineering. So it is a discipline where we experiment on a system in order to build confidence in how the system is capable to withstand turbulent conditions. And what that means is that it's not really chaos in the sense that we are injecting chaos in the system. It's more a matter of the system being chaotic. When we're working with distributed systems, as we've heard today, we're working with distributed systems all the time. They are chaotic by nature. So chaos engineering is a way of testing that chaotic, see how we can help the system improve. So, breaking it down, chaos engineering is about performing controlled experiments by injecting failure into our environments. So it's not only testing as we're used to it. So it sounds kind of scientific when we put it that way, and to be honest, it is. We're using a scientific method. We're creating a hypothesis and we're testing that through experiments. And chaos engineering is about finding weaknesses in the system. All systems we build, some way or another, have weaknesses. And by using chaos experiments, we're able to find those weaknesses, draw them out, and hopefully fix them before they create an outage. And as I said earlier, chaos engineering is about building confidence, both in your system and in your organization. Because when we do these experiments, we see how things work when there is an issue, when there is an error, as Ron talked about earlier, when we have outages. And by learning that, learning how our system behaves, we're able to build confidence, both in the system and in the people who handle that system. And the resilient part of a resilient system, it's mainly about the humans, the people who build it and the people who run that system. So let's look at some of the motivations behind doing chaos engineering, why we do it. This is a great quote by Charity Majors, the CTO at Honeycomb, that nines don't really matter if users aren't happy. Because we can have lots of SLAs, SLOs, SLIs, dashboards back and forth, but it doesn't really matter if they are green or red or yellow, as long as our users are unhappy with the way the system works. So, some of the motivations. Are our customers getting the experience that they should? Are they happy with how the system runs? Is downtime or issues in the system costing you money? We often say that nothing is free on the internet, and no matter then if we run a big e-commerce site or a personal blog, our issues with the system will probably cost us money somehow by not getting purchases or by less advertisement being shown on the site. Are we confident in the monitoring and alerting and observability that we have for our system? We've seen 2 talks today talking about monitoring and observability. And sure, we often have that set up for our system, but are we confident in that when something happens, it will show us the right data? Are we also confident in that our on-call people will get the alert when something really happens, when there is this big outage that we hope won't happen? And the organization in itself, how it's built, is the organization built to handle failure? We have that on paper. We perhaps have had incidents, but do we know that the organization is ready? Is the on-call person ready to wake up if the phone rings? And are we learning from incidents? When we have an incident, that's a great opportunity to learn. Learn how the system behaves, learn how we as an organization work. And the question is, are we using that data in the proper way to learn? Oops. My bad.
Do it.
Okay, so are we... Oh. Well, as Werner says, everything fails all the time. So, you've probably all seen this quote by Werner. And, well, everything fails all the time. Not my presentation, though. You know, most of you probably remember the big S3 outage back in 2017, I think, which took down big parts of the internet because Amazon had an issue with S3. And those big incidents, well, they happen more and more often, to be honest. Cloudflare had a big issue earlier in 2019, I think, which in the same way caused big parts of the internet to stop working. Google had issues with their services, which affected a lot of third parties because people are relying on Google accounts for authentication, for example. So everything fails all the time, and these big issues, well, they're not getting smaller, they are getting bigger. So, I think this brings us to perhaps the biggest motivation, that we shouldn't ask what happens if a system fails, we should ask what happens when it fails. Because it's gonna fail, sooner or later. chaos engineering then helps us reveal what happens when it fails. So let's look at how to run some chaos experiments. We're not going to deep dive into this, just cover the basics. So we have time to look at some demos instead. So we do it by following a few quite simple steps. Start off with defining what's called a steady state. And the steady state of our system is the way the system normally behaves, the way it behaves each and every day, normally. And to know that, we need to have metrics. We need to have observability into our system. Ara talked about it earlier today about the system metrics and the business metrics. And both are important. But I would say that when it comes to this, how our users are happy or not, well, the business metrics are probably the most important ones. Are we having enough sales each day? Are people clicking those buttons enough? And finding those metrics will give us the steady state of our system. And based on that, we form what's called an hypothesis. And this is, I guess, the scientific part of it. So we consider how our system works and what might happen. And to form the hypothesis, we use what's called what-ifs. What if the database is down? What if DynamoDB stops working? What if Bob isn't in the office? What if Lambda has latency? We try those what-ifs, and based on that, we create a hypothesis. And the hypothesis is formed like if this, then that. So if DynamoDB goes down, my system will go to the fallback, which is text files or whatever. So we perform, or we create that hypothesis, and then we find ways to create experiments based on that, which is the next part. So we plan the experiment based on the hypothesis. We get some smart people gathered in a room, people who know about the system. And based on the hypothesis we have, we sketch it out, whiteboard the experiment, and decide upon how do we perform it. How do we remove DynamoDB from the equation to see what the system actually does? We probably have a lot of code to handle those issues, or we have interconnected services without code. Well, how does it behave in those cases? So we plan the experiment, and then it's time to run it. And when we run the experiment, we talk about something called blast radius. And the blast radius is how big of an effect can this experiment have on our system. And of course, we don't want to create a big issue that could cause harm to our users. So we start off with the smallest possible experiment. And the blast radius can be of in different ways. It might be that we do an experiment that only affect 1% of users, or only affect Norwegian users, which is fine. Or we only affect, I don't know, Monday morning between 7 and 8. So we find ways to have the blast radius as small as possible. When we run the experiment, one important thing there is to have a stop button. So some way to always abort the experiment when it's running. Because we do find quite often that the behavior of our system is quite far from the behavior we were expecting. So we do an experiment, something unexpected happens. So make sure to have a way to abort the experiment. And then when we have run our experiment, we've done it, we've stopped it, then we take those metrics once again. We look at what happened in our system. And based on that, we can see that, well, we had spikes in CPU on system X, or we dropped in sales in a specific country, or whatever happened, whatever we experimented on, will get results based on those metrics. And this is the important part then, to learn from these results. So we will probably end up with quite a lot of bug fixes, with things to improve in our system, or we discovered that we didn't have a fallback. The fallback we had didn't work. Or we relied too heavily on cloud provider X. And the next step then is to do something with this result. So we can either just abort and fix those issues, or if the system behaved as expected, we just scale up the experiment. The blast radius we set before, well, let's include more countries, let's include more users, or 5 Lambda functions, whatever the blast radius was. So that's the steps for running chaos experiments, and we follow those over and over again to improve our system and to grow our confidence in the system. So let's move over to the serverless part then of chaos engineering. And a lot of you probably think that, well, are there challenges with serverless? And there are quite a few actually, and many of them are the same ones as we see as benefits. So this is the AWS definition of serverless, which has been around for quite some time, that serverless allows you to build and run applications and services without thinking about servers. And I, for one, am a big fan about this part, without thinking about servers. Because I don't like to think about servers, frankly. But then we get to this one. There are still servers in serverless. You know, the song by Bob Dylan. Well, there are servers, Bob. The thing is that we just don't manage them. And that is part of the challenge with serverless. So let's look at those challenges. So we have no servers to manage. And that means that we can't really do experiments on the infrastructure, which is basically where chaos engineering started out. Netflix more or less randomly shut down EC2s. Well, we don't have any EC2s to shut down, which makes it harder for us. And the underlying failure modes are really unknown for us. We don't have any documentation that says that, well, this might happen with the infrastructure, because we are led to believe that we don't have to worry about the infrastructure, but I think we should worry about it, just a bit at least. Less heavy lifting. One of the pros with serverless, but the thing with heavy lifting is that every time someone set up infrastructure of some sort, be it physical servers, virtual machines, Kubernetes clusters, people tend to learn a lot about that service. They learn what the failure modes are, what are the issues, what are hard things about this infrastructure. And in these cases where we tend to focus on configuration and code, well, once again, we don't get to know those things about the underlying infrastructure. There are so many services to choose from. Today, based on your definition, anything that is fully managed, more or less, is called serverless. Well, it doesn't even have to be fully managed. Kind of managed means that it's serverless today. So there are so many services that we use and that we interconnect with each other. And the more services we have means that we have more configuration, we have more security options, and many of those are good, of course, but it also means that we are able to introduce configuration issues and security issues into our applications. So we need to have more control over those parts of the applications. Yeah, so by being able to, it gives us the ability to configure each and every service and each and every function within our application by itself. We have issues with configuration over and over again. And the architectures that we build today with serverless are in many ways more granular than anything we've seen before. And that means that by being so granular, it also is more chaotic by nature, because the architecture in itself is chaotic. So with this, though, I'd like to say once again that chaos engineering, I think it's a perfect fit for serverless because it helps us draw out those chaotic parts by doing these experiments. One slide ahead. So chaos engineering, by being so, or serverless, by being so chaotic in itself and granular, it is a perfect fit for serverless. And I think we can all benefit from using chaos engineering in that way. So let's look at some chaos experiments for serverless so we can see what I'm talking about. So these are some things that we see quite often in serverless applications, that error handling, which Ron talked about earlier, it's not always properly handled by our applications because we don't always get those errors. So we don't know exactly how our system behaves. So we have errors that perhaps show up once in a million invocations for Lambda, which means that we aren't able to test it properly. So by doing chaos experiments and introducing errors into our applications, we're able to see exactly how the system behaves when we have those errors. And AWS, at least, has moved a lot, I think, in the recent year to help us handle many errors by introducing, for example, SNS DLQs is a recent addition, to have dead letter queues for SNS. And also by introducing Lambda destinations, which means that we have less code to worry about. We had to build that logic ourselves. But still, even though they introduced this, I, for one, like to know exactly how the system behaves. Even though it's a managed setting from AWS, I like to test to see that DLQs work exactly as they are intended. Something that has been talked about a few times today as well is timeout values. Timeout values for our Lambda functions. And that comes, it becomes more important when we interconnect services with each other. So we have services that are dependent on each other. And everything usually works just fine as long as there isn't any latency. But what happens when we get latency? Because sometimes, not that often, there is latency in Lambda. There is latency in DynamoDB and so on, to test how your application handles latency. And event-driven applications is more or less the norm today. But how do we handle issues with events? If we use EventBridge or SNS, SQS, and so on, what happens if there are issues with those events? Are we queuing them correctly? Are we storing them correctly? Can we retry them, and so on? So those are also things we can test by using chaos experiments. And fallbacks. We rely on services to work. We rely on DynamoDB, once again, to always be there. But sooner or later, something will happen that means this DynamoDB isn't there. So make sure to have fallbacks so we can see how the application works. And failovers. Goiko talked about multi-region and global scale earlier on. Failovers isn't always for having regional outages to make sure that that works. It might also be that we have an ISP with latency issues, so every request takes longer. One of the regions for AWS or Azure or Google has an issue which means that we are unable to connect to that from our ISP. So failovers helps us in more ways than just having data closer to the user. So those are some of the areas that we usually look at when we create our experiments. So let's look at some more practical ones then. So this is a really simple architecture with a client calling S3 directly or through API gateway. 2 Lambda functions behind the gateway, which in turn then stores or retrieves data from S3 or stores and retrieves data from DynamoDB. Really simple. So things we can do then is we can inject errors into our code, as I said before, so that instead of having the 200 response from API Gateway, it returns a 404 or a 502 or a 501, so that we can check how our application behaves when we get an error response instead of the normal 200 OK. We can remove downstream services, like S3. How does our application behave if S3 doesn't respond to the Lambda function, if it doesn't return any data as it's intended to do? We can, of course, alter the concurrency of functions, so it isn't able to spin up as many functions or concurrent functions as we need. We can restrict the capacity of DynamoDB tables, and we do this not perhaps, well, it might be configuration errors, of course, but there might be issues with DynamoDB that means that the capacity of DynamoDB is restricted. So by testing this, we're able to see how does our application behave. Other ones, of course, we can introduce security policy errors. They happen more often than not, I think. So we can introduce them ourselves to see what happens if the client is unable to retrieve data from S3. Of course, configuration errors like CORS for API Gateway. We can introduce different types of service configuration errors for every type of service we use. And these are quite easy to perform, these experiments, because since we have APIs and CLIs for all services, we're able to just by one CLI command, we can introduce a configuration error, and the stop button in that case is just another CLI command. And then we're back to normal state once again. And sometimes we use the disk space in Lambda functions, or in Azure or functions or cloud functions. What happens if there are issues with the disk space in Lambda? Really doesn't happen often, but it might. And there might be issues with your code as well, which means that it fills up that disk. So we can introduce disk space errors by filling the disk in our Lambda functions. And latency in functions. This is more or less the first experiment that was created for serverless. And Jan Kui, our keynote speaker today, he wrote a great article on this a couple of years ago, where he created sample code and so on for it, which has been reused over and over and again. And Adrian Hornsby, evangelist for AWS, has written a Python library for using those types of experiments as well. And by using latency, we're able to simulate those cold starts that has been mentioned a few times today, to see how our application behaves if there are cold starts. We're able to create some type of cloud provider issue by adding latency so that every request takes 50, 100, 200 milliseconds extra. We can, of course, simulate runtime or code issues that would give us latency as well. Integration issues with third-party services or downstream services. And we can check our timeouts to see that it is configured correctly. So those are a few different, or quite a few different experiments that we can perform, and we can perform them quite easily. And there are some tools that can help us with this. Gremlin is a company that offers a SaaS solution for chaos experiments. It is mainly based for VMs and Kubernetes and containers, but they have something called Alfie, which is application layer fault injection, where you can introduce errors into your code. There is the open source Chaos Toolkit, which isn't built exactly for serverless either, but they have started to create modules for that as well. Then we have Thundra, the APM solution. They have a feature within their tool where you can inject error into the application by using the wrapper or the agent that they have. So you can do that through their APM solution. Then we have the Chaos Lambda Python library that Adrian created. which is starting to get used quite a lot today to test your Python functions. Then we have the Failure-lambda NodeJS one, which I've created, which helps us to create experiments for Node.js functions. And just a few hours ago, I published a failure Azure functions one for Node.js as well. I'm not an Azure user normally, so probably works so-and-so, but will get improved. So try it out if you use Azure, the 1-2 persons who did in the room. So short about Failure-lambda then. It's just an npm package for Node.js lambdas. So you just install it, and you wrap your handler. The code isn't important, so you don't need to view that. But you import it, and you wrap your handler. And through that, you're then able to configure the failure module using parameter store. So it's simply a JSON that tells you if it's on or off and what failure mode you want to use. So it has a bunch of different failure modes: latency, status code, that is, you're able to respond with a 404 or 502 or whatever you choose. You can create exceptions in the code, and you can fill up disk space, and you can blacklist. And blacklist means that you're able to block, for example, access to S3 or DynamoDB or other services through the Lambda handler. So, serverless chaos demo then. I created a simple site just to show off how this could work. So it's demo.serverlesschaos.com. So it's a simple static website which calls Lambda functions to retrieve data. The architecture looks like this, pretty much the same as we saw before. 3 different Lambda functions. They all do the same, all use the same code base, but we can then inject Lambda into each and every one of them by themselves. So they retrieve data from DynamoDB. So I'm just going to show you exactly how this works in a quite easy way. First off, we need, of course, to create the hypothesis for our experiment. And as I said before, we do it by what-ifs. So what if my function takes an extra 300 milliseconds for each invocation? What if my function returns an error code? What if I can't get data from DynamoDB? Those are potential three different experiments to perform for us. And the simple hypothesis is that if we inject failure to functions, then my application will use graceful degradation. So it will still work. Users will be happy. They perhaps can't get all of the functionality from the application. So, demo time. There we go. Is it readable? Silence means yes. Okay, so as I said, there are 3 Lambda functions. And for each Lambda function, I have a different parameter in parameter store. And let's start with opening the site as well. There we go. Okay. So it looks like this. So there are 3 different images. Each image reloads every 5 seconds. So it calls the API gateway, which invokes the Lambda function, which fetches data from DynamoDB. If this was a real application, we would probably build it a different way, but this is for demo purposes. So it calls every 5 seconds, retrieves a new image, and the images are retrieved from S3. And as we see right now, it works pretty good. 200-300 milliseconds for each invocation and 200 responses. So moving back to parameter store. And since this is a parameter, we could simply use CLI commands as well. just use the AWS SSM put parameter to update these parameters. But I guess it's better to show it in the UI. So this is one of them. And as you can see, is enabled false right now. And it's set to failure mode latency. It has a rate of 1, which means that it will inject failure on every invocation. If I set this to 0.5, it will inject error on roughly half of the invocations. And I can set the latency, minimum 100 milliseconds, maximum 400 milliseconds. So let's update this one and enable it. Is enabled true. There we go, updated. So now, for each invocation of function 1, it should still work, but it adds between 100 and 400 milliseconds latency to that function. So we are still within the timeout values, so it doesn't throw an exception or an error. But as you can see, now it's 600 milliseconds, 640, and so on. So this gives us the ability to test how does our application work when there is latency within Lambda. So let's look at one of the other ones. Let's take number 2. And to that one, let's change it to true and failure mode. Status code. And by using status code, we're able to insert a different response code instead of the 200s we got now. And save. Still, the rate was 1, so it will be on every request. There we go. So now it says status 0, but that means that we get an error response. So it doesn't work, it doesn't reload the images, because every response through API gateway, I don't use a MacBook Air, so that's not me. If we saw the screen, we would still see the error messages. I didn't inject this failure. Cool. OK. And the third one, we could inject some other type of error there. Whose is it? Sorry?
How can you actually inject the error into the by changing parameters?
Yeah. Since I've wrapped the handler, everything that is within my handler is going through the code that the library uses, and it just changes the response that you would return to the one that I've chosen. So in this case, 404.
The function, the code of the lambda function actually changes when you change the parameter.
Well, if it is enabled and using a specific failure mode, it goes through more or less different ifs. If this is enabled, then respond with the code you have chosen. Yeah. Let's watch Netflix, since I talked about that. OK, but no? Any other questions while we wait for this? Crystal clear? That's mine. Thank you very much. OK, should we see the last one as well? My bad. There we go. OK, let's change the last one as well. I don't have a mouse pointer. Come on. There we go. OK, parameter 3. And in this case, let's enable it. and use failure mode blacklist. Blacklist means that we are able to, by adding different values here, we're able to blacklist those requests. So in this case, everything from the S3 API and from the DynamoDB API. Did I change it to true? I did. And save. Okay. So now it shouldn't be able to call DynamoDB anymore. And we should probably see that by it not changing the image on function 3, which it doesn't. So we have now blacklisted DynamoDB and S3 calls. So fairly simple way of injecting errors into our functions. And function 3 keeps running, but it just doesn't return the data. And my application doesn't handle those errors very well, apparently. So let's go back to the presentation. Last few slides. Demo. Okay, so to recap this, remember Werner's words, everything fails all the time. Just count on things to fail. Serverless in itself doesn't make your application resilient. You have the building blocks, but you have to make sure that the application is resilient, either through your code or through the way you architect, or combination, hopefully. Less code is always better. Chaos engineering helps us find weaknesses and fix those before they turn out to become a big outage. And chaos engineering is about building confidence in the organization as well as in your application. And it's really not rocket science. As I've shown, it's easy to get started with it. The experiments doesn't have to be really complicated to perform. You can just do it through the CLI if you wish to. So, if you want some more, there is a Twitter bot, Serverless Chaos, which you can follow to get tweets around chaos engineering. Try out the Serverless Chaos demo app, of course. It's open sourced, so you're able to play with it yourself. The Failure-lambda NPM module, use that, or if you're into Python, use the Chaos Lambda one from Adrian. On my site, I have some YouTube videos and other repositories around chaos engineering for serverless. And there is a Slack channel or a Slack for chaos engineering. Join that and ask questions and learn from the community. And with that, I thank you.